Okay, so in the case of beryllium, this would be that outer shell, right? These are the valence electrons. So that outer shell, we have 2 valence electrons. Is that true? Selena, beryllium.
Yes.
Do we have 2 valence electrons in that outer shell?
I want to say yes.
Okay. Are you confident?
Yeah, I want to be confident.
Okay, so you're giving me all these loaded answers today, right?
I
But
mean,
yes, beryllium has 2 valence electrons, right? Both of them are located in the 2s, right? So they have 2 valence electrons those are the electrons that we're going to be able to use for bonding, those valence electrons, right? So this is what beryllium looks like when beryllium is all by itself. Now, when beryllium gets ready to covalently bond with something, what it wants to do is it wants to try to find an energy level so that will be attractive for itself and its partner. So it's going to form a hybrid, because right now, beryllium is right here in terms of the energy level. It's low, right? But remember, ultimately, beryllium wants to be happy. It wants to be to a state, although beryllium's happiness is a little weird compared to everybody else. Beryllium is cool with just having 4 electrons around it, right? So beryllium is looking to try to get 4 electrons so that it's just sharing another 2 electrons. So it wants to try to make itself sexy enough, right? And one way of being sexy, if you're an atom, is to kind of lower that energy state. That makes you real sexy, right? Because then you're like, hey, come on, this will help you be a little bit lower in energy. It'll make you, you know. So beryllium is like showing a little leg right now. Okay, you guys get that? So what beryllium does, it hybridizes to make itself a little more attractive, a little more wanting for something to react with it. Okay, so then that case, it allows that other atom to be in another energy level, a lower energy level than it would normally be. Okay, and so that is the significance of hybridization. What was that?
Sorry, because the lower the energy, the more stable you are, right? Or like the less energy that you have to utilize.
Exactly, right?
Okay.
You know, you think about it. In most cases, most of you guys get together. I mean, of course, he's a hottie, right? Yeah, if he's a hottie in a high drama, that isn't gonna last. You know, it may last for a couple of years, and then eventually, like, dump that loser, right? And then you're going for that guy that's like, okay, he has a job, he pays his bills. You know, you're looking at that, right? You know, you're looking for that provider, right? Or she has her job, she pays her bills. You know, so
I love how you bring reality to situations like this, because it makes it so much easier to understand.
But I mean, ultimately, it's funny, but reality for the electron is very much the same as us. You know, it's at the end of the day, it's about trying to survive and trying to do it efficiently, right? We're not, you know, we're always trying to find that perfect, you know, fun work, you know, work balance. We're always trying to find that perfect way. So you're always looking for that level that makes it a little bit easier for you, right? And so that's exactly what's happening here. It's the same thing, okay? And so beryllium says, okay, so, you know, since that's the case, what I can do is I can sit there and grab one of these guys, right? And I can mix it together. And if I mix it together, it's going to be at an energy level between the S and the P. And so when something wants to react with me, right, I have this spot open for it to react with me so that they can put their electron in there, right? One of them could put their electron here and the other one could put their electron there, and we could be good to go. And it'll be a lower energy state than putting them both in the P. So it helps beryllium just as much as it helps that other atom when they want to share the electron. Does that make sense? Because it's lower than going up in this energy shell, right? By a little, it's lower than that. So you're saving, you're a little more efficient in that case. And so that's the rationale. And so literally, they take an S, they take a P, they mix it together, and then they get these guys, right? These little balloon nipple type of thing, right? And then this guy represents one sp orbital. This guy represents the other sp orbital. And we call it an sp because it's a hybrid between the S and the P. Does that make sense? So we take a 2s and a 2p, and we mix it together, and then we get a 2sp, right? So second energy level, okay? But really, they don't even call it a 2sp, they just call it an sp, okay? Does that make sense? They don't give you the energy level where it's at. They just kind of like understood. So we don't get confused thinking it's multiple, right? Does that make sense?
So you would never include your energy levels, like your level?
You don't
You
have
would just
to.
say SP?
Yeah, we just say SP. Yeah, because it's only going to happen in that outer shell. So you're not going to worry about any of your inner core. So,
Okay.
so it's always understood. Okay? Does that make sense? Selena, you're good?
I'm just slowly processing it. Every morning is really slow for me.
That's all right. You're not a coffee drinker, so I understand.
Occasionally, but
Occasionally, yeah. So we've corrupted you. That's what you're saying.
not.
In that chemistry, that morning chemistry got me. Okay. So now we have, in the case of sp2, that means we're taking 2 p orbitals. Okay. So now we're taking 1s and then 2 different p orbitals, and we're going to blend it together. So literally, we're taking these 3 here from, in this case, is boron, right? And it's going to do the same thing. It's going to form the hybrid to try to make the energy level lower than what it would be if it was just a 2p, okay? And then you get these hybrid orbitals formed. You get 3 of these nipple-like structures, balloon with a little nipple on the end structures. And then they will serve as spots for bonding. And again, this only happens when bonding is occurring. So hybridization only occurs when bonding is going to happen. Okay? Does that make sense?
You said SP2 takes 2s and 2p, or just the p?
No, 1s and 2p.
1s.
Yeah, you see the 1s here and 2p. Yep. So takes that this s down here and 2 of those p's, right? And then it mixes it all together and it forms, and these hybrids are all equal in energy. That's why they're all at the same level. So this represents our energy. Remember our energy diagram? All this is representing our energy diagram, and this is just showing you where hybridization falls between that, right? It's between that S and the P. Okay. Okay, so, and it's going to be, again, it's going to be dependent on that center atom that's going to be sharing. Okay, so beryllium has the potential of taking, because it only likes to have 3 attachments, 3 bonds, right? So it has the ability to attach 3 times. Okay, 1, 2, 3. Okay, so carbon has the ability of having 4 attachments. So what can carbon do? What will carbon do? So beryllium had 2, boron had 3, and now we're talking about carbon. What do we expect to happen with carbon?
There'd be 4.
What was that?
There would be 4.
4. Okay, so then in that case, so this, if we look at it, so for boron, that was 1, 2, 3. So then our hybrid would be called what? In the case of carbon.
Carbon would be SP4.
Would it be sp4?
So,
Because this is, boron was sp2, right? Because it has 1s and 2 p's. Then carbon would be what?
3.
sp3. That would be 1, and then there would be 3 of these guys. 1 plus 3 equals 4. Our 4 times. Does that make sense?
Oh,
Getting there.
Count up.
Okay. So, okay. And now we're gonna get a little hard here. Okay. So
why
if we
would I
look at-
just figured it out?
That's right. So I'm seeing sparks, you know, they're like little flashes that are coming out above your heads or through the screen, that black screen. I'm feeling it, you know. Okay, so if we have phosphorus, phosphorus has the ability of having 5 attachments, right? Because it's in that third energy level. It can use that d orbital. So what would phosphorus? So carbon had 4 attachments. Phosphorus can have 5 attachments.
Should be sp4.
Is there, wait, are there 4 orbitals?
But
Are there 4 orbitals in the p?
no.
Dr. Henry, we're supposed to be seeing a blue screen.
No, you're not supposed to be seeing a blue screen. Sorry about that. Give me 1 second. My PowerPoint crashed for a second. Okay, you guys see it?
Yeah.
Okay, good. Okay, so because we know that the p has how many orbitals again?
3.
1, 2, 3. So we've occupied all 3 of them. So then we need to do what if we're going to get 5 attachments?
Make
Is this
another.
where the d orbital comes into play?
This is where the d orbital comes into play, right? Because after the p, what comes next? The d, right? We got the s, the p, and then we go to the d. Is that correct? So then in that case, we would have the s, p3, d, hybrid orbital. Does that make sense? Okay, don't worry. It'll get there. It'll start clicking in a minute, okay? Okay, so if we're looking at the center atom, this center atom has the ability to have 3 attachments. If we take an S plus 2 P's, so that's total of two orbitals for the P, 1 orbital for the S, that equals 3. That represents the number of attachments that that particular atom can have, right? So the hybrids, the most hybrids that you can have for boron is 3. Does that make sense?
So you're just focusing on valence electrons.
Mhm.
So with phosphorus, I was like, but there's no D in like the electron configuration. But now I see focusing on valence electrons and then adding up the sp3d, that
That's right.
equals 5, which is the 5 valence electrons. So
That's right.
that makes
And-
sense.
And we know now you're gonna see my blue screen on purpose. Hold on, let me see if I can get there.
So then if you move further, would you have an F
Yeah, we could have
eventually?
a hybrid. We could have a hybrid with the F as well
Okay.
eventually. Yeah, that is a possibility. We'll never get there. We haven't got to that point ever. In reality, not yet at least.
Right. Well, that's like the hypotheticals that we
wood.
talked about.
Knock on wood, but yeah, yes. So
Okay.
can you guys see my P table?
Yes.
Okay. Okay, because remember, we're in the 3rd energy level here, right? And we know that 3D, 3 is that energy level, which starts here. That guy is actually available for these guys to use, right? And so they make use of that. Okay. So if we had sulfur has the ability of having 6 attachments. So
I thought that was a statement, not a question.
there's a question that goes with that. So sulfur has the ability of having 6 attachments when it needs to, right? So if that's the case, if it could have 6 attachments, then what is going to be the hybrid orbital that sulfur would make to have those 6 attachments?
So then would it be sp3d2?
That is correct. And let's see. Iodine has the ability of having 7 attachments. So in that case, what would be its potential, its hybrid that would form?
You just increase your D, so it'd be D3.
Are you with me, Matt?
Yeah, I'm paying attention.
I get paying attention, but are you with me?
I'm trying. I'm kind of with everyone else. Or I'm a little slow in the mornings, but I'm paying attention. I'm taking notes.
Good, good. Okay. So are you guys seeing this trend?
Kind of, but I'm not really putting it together for some reason.
Okay. So boron, which boron has basically 3 valence electrons. It likes to have 3 attachments, right? Boron, remember, our exception likes to be like this. It's like, hey, I'm cool with being not having my octet. Remember that? Beryllium.
Yeah.
Who only likes to have 2 attachments, which is an odd metal. It usually doesn't like to form ionic bonds. It prefers forming covalent bonds. Right? So this one is 2, so that's just sp. This guy is sp3. I mean sp2. Carbon, sp3. Are you with me?
Yeah.
Good, good. Okay. Okay, so let me show you that in context, right? Okay. So this is an example where we're using sp2, right? Now, the other thing that we want to say about the hybrids, there's one other thing that we had mentioned about the hybrids that I should have pointed out earlier. Hybrids are only going to be able to form sigma bonds, right? Where you have that overlap. They're not going to form a pi bond, okay? They never, ever will form a pi bond, okay? And that's what we want to also keep in mind as well, too, okay?
What's never
So-
gonna form a pi bond?
What was that?
What's never gonna form a pi bond?
The hybrid. The hybrids. So your sp whatever. So sp is only going to be able to form sigma bonds. They're not going to form pi bonds. So in other words, they're not going to have 2 p overlaps. It's only going to be either a p overlapping with an sp, or it's going to be in this context, or it's going to be a S overlapping with an SP or SP2 or SP, or just a hybrid, we'll just say in general. Does that make sense? So you will never have this happen, right? So that pi bonds can never be hybridized. Does that make sense? So anytime that you have a double bond, one of them could be a hybrid, but the other one is going to be a pi, right? Because this guy is sigma pi, right? 1 sigma, 1 pi for a double bond. So one of these bonds will represent the sigma. One of those guys will represent a hybrid from that N. So this guy, this is sp2, right? Because this here is going to be one of the lone pair will be in the hybrid. This guy will be in the hybrid, and just one of the bonds there will be in the hybrid. The other one has to be a normal p orbital that's used for that. Yeah, that little Cassie.
No, I'm just processing. So when you say a hybrid, you're only specifically talking about the sigma bond, but you can have the pi bond there too.
Yes, that's right.
Okay. Okay.
Yeah. So hybrids will never form a pi bond though. So you'll never get anything like this. Because that nipple's too small for it to happen, you know? So you'll never get that overlap. That would cause issues. So that will never happen.
Right. Okay.
Okay. And that's one of the reasons why it has to go end over end. So that's the same thing that it's here, right? In this case, this carbon here, though it has 4 attachments, because it's forming that double bond, it's only going to use the sp2 hybrid. And then same thing with each of these carbons. This guy is going to be sp2. And this guy's going to be sp. So it's going to have an sp2 hybrid going on. Does that make sense?
Yeah.
In a way, it does.
In a way, it does.
I'm just trying to process everything.
Okay. Okay. Okay, so we talked about in the case of carbon, like in the case of carbon combining with CH4. So if we have carbon, oops. CH4, not CHP.
Okay. I was like,
Brain, you know, again, coffee's just hitting my bloodstream itself. So if we drew that energy diagram, so for carbon alone, what would it look like?
so it's 1s2, 2s2.
Now remember, if it's in the core, we're not worried about it because we're only worried about those valence.
Oh,
We're just going to
so
ignore them.
so it's 2 p4. No, that's not right. I mean, there's 4 valence electrons.
Okay, but where are they located at?
In the p.
Are they all located in the P?
Are 2 of them on the 2s?
Okay, you're gonna have 2 in the 2s, because remember, we're gonna still obey the rules, right? So you're just looking at the valence. So we know that 2 of them are in the 2s, so we have to pull up the 2s first before we can get to the 2p. And then those other valence electrons,
It would
sorry, those
be
other valence electrons,
the first 2 in the
okay,
p.
because we're gonna obey Hund's rule and Pauli exclusion principle, right? Okay, so this is what carbon alone looks like. So in the case of CH4, we have how many attachments?
4.
We have 4 attachments. So that means that we need to have 4 hybrid orbitals. So if we're going with 4 hybrid orbitals, each one is going to be called,
sp4.
is it SP4?
No, 3, because it's
SP3.
you add 1. The
Yep.
s is 1. It was a total of 4.
That's right. So in that case, we're taking all of the ones in the P and that 1s, and we're mixing them together to make this one energy level. And then we're putting 1 electron in each of those. Hundred, right? Okay. Okay, so then now it's ready to bond with the hydrogen. Okay, it's like it's looking sexy. Hydrogen. Hey, look at this. Low energy. Come on. You know you want it. You need that one electron. You know. Okay. So simple, not too hard.
Wait, so during the whole hybridization process, are you like spreading out all the electrons as much as you can?
Yes, if you need to, right? So like here, we don't need to because we have 3 attachments, right? We have 1, 2, 3. So we don't have to spread them all out. We just have to spread out the ones that we need. Does that make sense?
Okay, and those would apply to like the valence electrons, right?
Yeah. You take your valence electrons and you're also going to take into consideration your electron pair geometry, right? 3 attachments, 1, 2, 3. That's your electron pair geometry, isn't it?
Yeah.
And this guy would be called, since there's 3 attachments, for your EPG, electron pair geometry, would be called what in this case?
3? Or oh no, wait. Like the trigonal thing.
That's your electron pair geometry. So what is the geometry of this? What would be the geometric shape of this guy?
Trigonal planar.
Trigonal planar, that's right. Okay. Make sense? So it has 3 guys, 3 things that are going to be attached. Okay. So then its hybridization on that nitrogen would be sp2. 1, 2, 3. Okay. So what about CH4? What would be the EPG for CH4? Let me draw it out for you. I know you guys are struggling a little bit this morning because your coffee hasn't kicked in.
Tetrahedral.
Is that tetrahedral? Because that's 4 attachments.
Okay, that's right. Tetrahedral. And it has, you said, 4 attachments. So then its hybridization of that center atom would be what?
4.
Okay, so then what would I write?
So you would say sp3.
sp3. Okay, so what about phosphorus in this case? Or phosphorus in this case?
Trigonal, right?
Trigonal bipyramidal or bipyramid
Okay,
for the
trigonal.
5CO, I think.
Okay. So would it be for both? 5 attachments? Or EPG?
No, because you have the lone pair on top of the other one.
But we're not talking about the molecular geometry. We're just talking about the EPG.
Oh, so
So would both structures have the same EPG?
trigonal.
Right. Because it's 5 attachments, right? That lone pair counts as an attachment. So it would be trigonal bipyramidal. Okay, does that make sense?
Yeah.
Okay, so then that would be a total of 5 attachments. 5 attachments. So then what would be the hybridization on that center atom?
SP4.
Are you sure?
No, it'd be 3 with a D.
Okay. So you know that's going to be on the test now because you said it. You're going to have a multiple choice. It's going to be SP4.
My confidence
And then-
was knocked down like a blocked basketball shot.
So we know that you're always going to be limited by the number of orbitals that you have for that particular subshell.
Right, because there's only 3 in the P.
That's correct.
Yeah, now I get it.
Okay. Okay, clear. Okay, let me clear this. How are we doing? Okay. So here, these guys are all going to be SP3, right? 1, 2, 3, 4, 5 attachments. SP3. This guy, 5 attachments. 1, 2, 3, 4, 5. 5 attachments. SP3. 1, 2, 3, 4, 5. 5. Sorry. SP3D. 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 5 attachments for all of these. All these guys are going to be trigonal bipyramidal for their electron pair geometry. And again, we're looking at the center atoms. Okay, so now I have a question for you. What if I have something like this?
Dang. Stop adding.
Okay, I have something like this. So what do I have to do in this situation? How many center atoms do I have?
Would it be the 2 carbons?
Would it just be 2 carbons?
So then it'd be the 4 carbons because they're all the center.
They're all in the center, right? So they would all be considered center atoms. So we'd have to do one. We'd have to figure out the electron configuration for all of them. So we want the EPG for each one of those. Electron pair geometry.
Tetrahedral, right?
For the first one, it's tetrahedral.
One, 2, 3, 4, 5. So the other one is trigonal bipyramidal. Or the
Is it?
second one.
Are you
Well,
sure?
There's 5, right?
Count how many attachments?
1,
Literal
2,
attachments.
3, 4,
1, 2,
5.
3, 4.
Oh, I counted each
Oh,
bond. Dang it.
Actually, this is wrong anyway. Let me fix it because there's a double bond there. So it can only have 4 around it maximum. So there we go.
So then that's
Good eye.
trigonal planar. No, what is that one?
1, 2, 3.
So it's trigonal something.
You said trigonal planar? Trigonal planar is right.
Okay. It's blurry. It'll be the same for all of them for the remaining, right?
That's right.
There's 3.
Yep. What if we did this? Let's see. Let's do. Okay, what if we did this?
That one's 2, right? So linear.
Okay. Okay, so if we were talking about the hybridization, I'm going to write that in pink. So what would be the hybridization of this center atom? This right here.
SP3.
What about this one?
SP2.
And this one?
SP2.
And the last one?
SP.
Piece of cake?
Mm-hmm.
Yeah, I think I get it now.
Okay, so for these guys, since these guys are all going to be sp3d, here's my D, sp3d, all right? This is what it's going to look like, right? So these are all of the sp3 orbitals. That should be a total of, what, 5? So that's 1, 2, 3, 4, 5. 5 orbitals looking exactly the same. This guy would be sp3d2. So in the case of sulfur fluoride 6, 1, 2, 3, 4, 5, 6. And we know that this structure is octahedral, right? Right, 6 attachments, octahedral.
Yeah.
Okay, so when you're trying to figure out and assign the hybridization, the best thing to always do is, first thing, draw your Lewis dot structure. You saw what I did with that long carbon chain. I drew my Lewis dot structure, and then it becomes easy, right? And then you figure out your, I like to figure out the number of attachments, right? Or the electron pair geometry, okay? So then I figure out the hybridization, because then it makes it easier to figure it out. If there are 4 attachments, I know that's going to be what?
SP3.
sp3. If there's 2 attachments, then it's going to be
SP.
okay. Make sense?
Yeah.
Okay. And so this is just confirming exactly what I told you. So number of attachments or regions of electron density, right? 2 attachments. Oh, it's linear. Oh, SP. 3 attachments, trigonal planar, sp2. 4 attachments, sp3, tetrahedral. Okay. Good.
Yeah.
Okay. Good. So now let's talk about some other aspects of. So remember when I said things that are in the same group behave very similarly, right?
Yep.
Yes.
Did I say they behave exactly the same way?
No.
No.
No. Okay. So one of the things that we're going to have to also take into consideration is that things in a group behave very similarly, but there are going to be those minor differences, right? One of the differences, like say, for instance, oxygen. Oxygen, in terms of size, is oxygen and sulfur the same size?
No.
Which one is bigger?
Oxygen. Sulfur.
Sulfur is bigger, right? And I believe we have sulfur, then we have selenium, right? So selenium.
You were kind of mumbled. What did you say, Dr. Henry?
After sulfur, we have selenium. So who's bigger between sulfur and selenium?
Selenium.
And then after selenium, we have tellurium. Who's bigger between sulfur and tellurium?
Tellurium.
Okay. So the thing is that as we got bigger, certain things are going to happen, right? So that means that these atoms are getting bigger. So that means that the attachments that is formed is going to be further away from the nucleus, right? And since there's going to be further away from the nucleus, it's going to have an effect, right? And can you guys see my screen? See my screen?
Mm-hmm.
It's got
Okay.
3 diagram.
So we have water, we have sulfur, and we have tellurium. All of these guys are in the exact same group, right? They behave similarly. Like, look at the shape. The shape is very similar. But if you look at the angle between them, they're going to be different. These guys are going to be further away apart because it is in a tighter, it's really close to the nucleus. So these guys are really, they're bumping up against each other. But the further away you are, right, then you have less probability of bumping into each other. So as we go from water to dihydrogen sulfide, the angle can actually get smaller. And then as we go from dihydrogen sulfide to dihydrogen telluride, it gets to 90 degrees, right? And the reason why that happens is because now you're so far away from each other that the probability of the two atoms, the 2 hydrogen atoms, right? And then you had your lone pairs that are sitting out here in the back, both of these have 2 lone pairs. The probability of these guys interacting with each other is going to be so much less, right? Because it's so big, it's kind of like having this big old circle and then having the distance way out. So it doesn't have that nuclear effect the way it should, because that nucleus is way in the center, where here these guys are so tight, it's so short that everything's kind of packed together. So it's kind of like really, really tight. This guy is going to be still a little tight. And then this guy is going to be so far away that it's not going to really have an effect. Does that make sense? So those lone pairs don't affect the pushing of this as much as they did in this case, because they're so tight on the atom. Does it make sense? So then in that case, this guy here, right, is going to have a bigger angle compared to this guy, and then compared to this guy. Because these guys, this guy is going to sit there, okay, we can't get too close. We're going to be limited by what's happening here. These guys, okay, we can't get, too close still, but we can get closer than here because we're a little bit bigger. Does that make sense? Yes, no, maybe?
Yeah.
Okay. So our bond angle, because remember I said our bond angle is affected by those lone pairs, right? Because normally this guy would be, because this would be a tetrahedral, right? This guy would be 109. Okay, so then we could actually get our angle even smaller in this guy, because this guy is bigger in the context. And so we could play with that angle. We're not pushing so far because we're worried about these guys coming into contact with each other. We're less worried about these guys coming in contact with each other because it's so far away. Right? Because these guys help push on this, right? And I guess in a sense, they're going to still help push on this, but the distance between here, right, is going to be greater than it was in this case.
So they still push, but because of the distance, they don't push as much.
Yeah. So, well,
Okay.
They still push. Like these guys still push, right? So if we take a look at the way it pushes, they actually push more in the sense on here. But the distance, one of the reasons why that this guy is so big, like if you look at it, because altogether this has to be a total of, well, it's a 3-dimensional structure. Normally it's 109. If it's purely tetrahedral, it would be 109, 109.5 to be exact. So if this was a pure tetrahedral, it would be 109 distance between these two, then this guy, and then this guy, and this guy, right?
Yeah.
So what's happening in this case is that since it's 109, normally right here where they're all even. This guy is now greater, right? So this is greater than 109. The distance between here to kind of compensate because, you know, remember the 360 and all of that type of,
Mhm.
so this guy has to be greater than 109.5, where this guy is less than 109.5. This guy is much less than 109.5. So the distance between here is greater.
Greater.
Yeah. Now the distance between here is greater because we're bigger. Okay. And so that's
So-
going to affect it.
Does it directly correlate to the radius of the element then?
Yes. So there
Okay.
will be a direct correlation. So if we looked at selenium, if we had selenium, selenium would be right here, H dihydrogen selenide, right? So this guy would be between these two. So it'd be like 91 point something. 91 point, probably like 91 exact, somewhere in there.
Mm.
Okay.
And then continuing on, the was it polonium or whatever would be even less than 90, right? Because
Yeah.
you're growing. Okay.
Well, no, actually 90 is going to be your number. That's it. Because
So it
that's
doesn't go
gonna be-
past.
yeah, at
Okay.
90, it's kind of fixed. So
Okay.
either that or it won't happen.
Mm.
Okay. 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 So let's see. Ammonium sulfate is important for fertilization. What is the hybridization of the sulfur atom in the sulfur atom in sulfate in the sulfate ion? Okay, what does it look like? What is the electron configuration of this guy? I mean, electron configuration, the Lewis dot structure.
S is the central atom,
Okay.
and then you're gonna have 4 attachments. And I think you're gonna have 2 double bonds and 2 single bonds.
Oops. Oops. Okay. So that would be our Lewis dot. So then what would be the electron pair geometry?
Or so that's tetrahedral.
Okay. So we'd have tetrahedral.
Then you have sp3.
sp3 would be the hybridization. That is correct. Simple.
Yeah.
Okay. Okay, so here we have, what is the hybridization of selenium, of the selenium atom in selenium fluoride?
So selenium's in the center.
Okay.
Or 2, 4, 6, 8.
Any lone pair or anything?
Wouldn't you have a set?
Okay, a lone pair. One lone pair on the selenium. Okay.
5. So let's trigonal pyramidal.
Okay, so this guy would be, you said trigonal pyramidal. Pyramidal.
So then it's sp3d.
P3D. Okay,
So
that'll be a
that's
total of
2,
5
5.
attachments. 1, 2, 3, 4, 5. Good job. Okay. Challenging one. Urea. Let me give you a hint. Carbon's going to be the center. We have a nitrogen here. We're going to have a nitrogen here. And we're going to have a double bond here with the O.
Dr. Henry, can I ask us probably a stupid question?
Uh-huh.
Why is the oxygen in parentheses?
It's to let us know that it's attached to that carbon only. Right? It's not attached to that nitrogen.
Okay.
It's not a stupid question. It's the same question I asked. And because it's just trying to give you guidance. It really, all it is trying to give you guidance to the structure, right?
So it just states it's on the original or the first part, not the second.
That's right. It's not on the, nitrogen.
Okay.
If it was behind the nitrogen, that means that it would be on the nitrogen.
It would, okay. Would you ever have the case where the oxygen and nitrogen would be combined? So if it was just straight across or no?
Yeah, there are cases that happens, yes.
Okay. So then it's strictly
Yeah.
showing. Okay.
Yeah, so it's just trying to really just show you how it's structured.
Mhm. Okay.
Okay, so this is going to be the structure. So then of course we have. Okay. Okay, hybridization of your nitrogens and your carbon.
Nitrogen is tetrahedral.
Okay.
And it would be sp3.
We'll write that in sp3. Okay, this guy's the same thing.
Yeah.
And then your center atom.
Trigonal planar. sp2.
Okay, piece of cake.
Yeah, I understand it now.
Okay. Oops. Okay, so this is what acetic acid looks like. So what would be the hybridization on the 2 carbons? And then you can give me this oxygen.
Well, the first carbon is tetrahedral.
Okay.
sp3.
Okay.
Second is trigonal planar sp2.
And then the oxygen here.
1, 2, 3. It's tetrahedral sp3.
Piece of cake.
Getting there.
Okay, and you guys can see the way it's written. This O is just to let you know that this is double bond to that C, goes to that C, and and then that C is attached to this guy and that other C.
So when it's in parentheses, it's always a double bond?
Not always, but it's just letting you
Okay.
know it has that
It's
attachment.
attached. Okay.
Okay, so we've talked about the hybridization of our double bond, right? So in the case of the hybridization of a double bond, only the sigma bond is going to be hybridized. The pi bond is not. So we have to use P's for that. So that's what those P's come in handy for. All right, so we'll have those 3, and then we'll have that 1 available for that pi bond.
And that's why there's anytime there's a sigma or anytime there's a pi, there's a sigma with
That's
it.
right.
Bond. Okay.
Yep. Does that make sense?
Yeah.
Okay, so this is showing you in the case of acetylene or ethylene. So that's just double bond between the 2 carbons. Or actually, in this case, triple bond. It'll be C, ethylene, C, 1, 2, 3, C, H. Okay, so both of those carbons are going to do this. So you're going to have 2 pi bonds. You're going to have 2 sp bonds. And so that's going to interact with the hydrogen. These guys interact with the 2 carbons. And then that the other hydrogen. So that represents one of those bonds. And then those other 2 will be those 2 pi bonds that are forming. So here's your first pi bond. This is your second pi bond. Make sense?
Yeah.
Okay. So resonance basically is not going to have an effect on hybridization. So there's not going to be an effect on assignment, because, like, for instance, resonance basically means that we can alter the double bond between this carbon and that carbon, and then this carbon and that carbon. So that will be a resonance structure of each other, right? So resonance is not going to influence hybridization assignment. Okay. So you may get a question: does resonance structures influence hybridization?
Negative.
What's the answer?
No.
Okay, so here's an example of resonance, right? So what would be the hybridization
1, 2, 3.
of the S?
SP2.
Okay, piece of cake.
SP2.
Yeah.
Okay. Okay, so I'm going to stop here. So I need a few minutes of talking. Is that cool? And then we'll pick back up and we'll finish this chapter.
Yep.
Start. We're doing a lot. The rest of them are like examples of this. So there's one other thing that we have to go over, but let me stop my slides. Maybe stop sharing. Okay, so this Thursday there is going to be a woman history event happening at noon. I will be posting a flyer and the link and all that stuff onto campus later today. You guys will get extra credit points towards your exam. So this is another means of getting extra credit if you guys attend. I know some of you guys may not be able to attend. There'll be other events at other times. And so, but we want to try to show support for these events because it's kind of like what makes up our community. And plus, I'm going to go on a limb and say more than 90% of this class are women. So, or you represent a large proportion, at least of this section, are women. So, but that doesn't mean that the men can't be supportive of women as well. So. So I'll be there. Okay, are there any questions?
No.
Okay, at first I had an exam planned for the end of this week. I decided not to do that for two reasons. One reason is because my brain is fried and I don't know if I can make another exam that quick. And then also you guys have a lot of stuff on your plates because you have to finish your labs, you have to finish homework assignments, and you have to pay me $3 million. So,
Wow, you upped your charges.
yeah, I gotta make money some way, you know. Inflation, right? Or interest.
Okay.
I will see you guys on
Wednesday.
Wednesday. Yeah. Okay. I'll
Okay.
talk to you guys later. Have a good night.